Lesson 38, Sum, Difference, and Double Angle Identities. All right, so to begin with, we are just going to play around with this for a second, and we're going to see, does cos 30 plus 60 equal cos 30 plus cos 60, right? Like, can we divide it up that way? So let's see. So cos 30 plus 60 would be the same thing as cos 90 degrees, okay? And then that's going to be equal to, now we can actually write out what these are too, right? Cosine of 30 degrees, that's saying what's the x value on the unit circle at 30 degrees? Well, that would be root 3 over 2. Okay? Plus, and then the x value at cos 60, that'd be a half, right? And then the other part of this, so cos 90 degrees, well, that's actually just equal to 0, isn't it? At 90 degrees, our x value is 0. And 0 is not equal to root 3 over 2 plus a half, right? So this doesn't look like it's going to work out at all, does it? So that's kind of the only point I was trying to make there, is that that doesn't work. But we do end up with these different patterns here. So you see like cos 30 plus 60. That's one of our identities, right? So it's like angle A plus angle B. It would actually end up being equal to cosine of in that case, 30 degrees, and then times cosine of 60 degrees minus sine of 60, or sorry, 30, and then sine of 60, right? So it follows those patterns. So I won't get into like how we get these, but these are patterns that are going to emerge, and these are identities that we're going to utilize. Okay, so these again are on your formula sheet. We just need to use them in the right way. So let's see. This first one. So it's saying write each expression as a single trigonometric ratio. Okay, so a single trigonometric ratio would be like, I want to turn it into one of these guys on the left side. So, all right, I'm just looking for a pattern here. So if this is my first angle, 23 degrees, call that angle A. All right, and then this would be my second angle, 22 degrees, so I'll call that angle B. And then 22 again, so that would be a B, and then this would be an A. All right, does this show up, right? I'm just trying to match this up to one of these. All right, well, I see that I'm adding, so that kind of like limits it to this one or this one. And just, we'll see if this makes any sense. So sine A plus cos B. Yep, that's that first one. And then sine B plus cos A. That's that second one. So that means if it's in that form, then I can rewrite this thing as just sine of A plus B. And in that case, it was sine of 23 plus 22. So now that we have that, it's going to be sine, well, 45 degrees. Now, it wants it as a single trigonometric ratio, right? So that's really asking, what is sine at 45 degrees? So sine at 45 degrees is just root 2 over 2. That's the y value at 45 degrees. All right, next one. So again, I see a pattern here. We've got, one angle and then shows up again. And then that's a different angle and it shows up again. So I'm really looking at these ones, right, again. And they're easy to spot, I think, when you have them. So anyway, let's see if we can find that one. So this one's cos minus sine. So cos minus sine. So it looks like we're dealing with that one. And is it, angle A and then A again, and then B, and then B. So yep, that one lines up. So this is all the same as cos of A plus B. So this is cos pi over 4 plus 3 pi over 4. Okay, so this would be cos 4 pi over 4, which is cos, probably didn't need to do all that, pi. Okay, so cosine, like where is cos equal to pi? So like 180 degrees. Well, that would be -1, right? That's the x value at pi. All right, next one. All right, so in this one, again, it's just kind of spotting it, right? So we can see, yeah, tan 95, so I got angle, we'll call that A, and I'll call that B, A and B. So I'm just trying to match it up to the right one up here, right? So that one has a subtraction on the top, and then it's 1 plus that on the bottom. So this is going to be tan A minus B. All right, so from here, we're going to say this is tan A minus B. Okay, so this would be tan of 95 minus 35 degrees. So that's going to be tan 60 degrees. Okay, and where is tan 60 degrees? It's worth maybe looking at the unit circle for a second on this one. So where is tan 60 degrees? So I'm looking at 60 degrees here, right? I'm looking at this one. And remember what tan is. Tan is my y over my x, right? Or my sine over my cos. So it's really going to be root 3 over 2 over a half. So this is going to be root 3 over 2 over 1 half. And that would simplify to root 3. All right, so now just kind of going the other way. So now this one says, determine the exact value for sine 15. So let's maybe talk about for a second what the problem even is here, right? If you had a calculator, you could type in sine 15 degrees, and if you were in degree mode, it's going to give you a decimal, right? But we don't want a decimal. It says we want the exact value, right? So we're talking square roots, really. We're talking about some kind of ratio, something over something, but I want all of the digits. Now, typically, like if this was sine 45 degrees or something, right? If this was sine 45, then I would know the exact value of that. That would be root 2 over 2, right? That's the kind of answer we're looking for, is like root 2 over 2 or something like that, right? But the reason why we were able to do this one was because it was on the unit circle, right? 15 degrees is not on the unit circle. But what we can do is we can use numbers that we do know on the unit circle. So here's what I mean. Why don't we rewrite this as sine, and I'll do 45 because that's on the unit circle, minus 30 because that's on the unit circle, right? So I know the exact value of those things, okay? And the reason why I'm going to do that is because now I can use my sum or difference identities to solve for this one. So we've got sine A minus B. So which one is that? Let's kind of go up here. So sine A minus B. So that's this. So I can rewrite it all out as sine A cos B, yada yada, right? Okay, so this would be the same thing as sine 45 cos 30, and then minus cos 45 sine 30. Just following the formula, right? So just careful not to make mistakes on that, right? So that's A and B and A and B. Okay, so now why is that useful? It's because now that I have this thing split up this way, I know what the exact value of sine 45 is, right? That's going to be root 2 over 2. So this part right here is root 2 over 2. And then cosine 30, I also know what that is. Cosine 30 is going to be root 3 over 2. So at 30 degrees, the x value is 3 over 2. Minus, and then cos 45, so that's going to be root 2 over 2. And then sine 30, that's going to be a half. Okay, so now we'll just multiply this part first, and then this part, and then we'll subtract them. So the first one, so if you remember, we got a root multiplied by a root. Remember, you just actually multiply the numbers underneath, so that'd be the same thing as just the square root of 6 over 4. And then minus, and then root 2 times 1, this would just be root 2 over 4. Okay, so our final answer would just be, I'd have to leave the roots just as they are, so it would be root 6 minus root 2, and then just all over a common denominator of 4. So this would be your answer, right? Because it wants the exact value. This is exact, right? I don't want to put that in my calculator because then that's going to give me a bunch of never-ending digits, right? That's going to give me an irrational number that I would have to round at some point. So this one, since we're not rounding, that is exact. All right, wish I would have given myself a little more room there, but make this work. Okay, so now the next one, we've got, here, I'm going to write this out again. So we've got cos 7 pi over 12. I'm just going to rewrite this guy. So let's rewrite this as cos, and then instead of 7 pi over 12, these ones take a little bit more kind of fiddling with to kind of get the numbers so that they're on the unit circle. But let's try this one. So if we broke this up as 3 pi over 12 plus 4 pi over 12, right? So I know those are going to simplify, and hopefully they simplify to something on the unit circle. So you can kind of guess and check a bit. So just notice, though, that I kept the denominator the same and then just made my numerators add up to 7, right? So, all right. So yeah, if we simplify that down a little bit, that's going to be the same thing as cos and then pi over 4. And yes, that is on the unit circle. Plus, and then this simplifies to pi over 3. Perfect. I know what both of those are. So now let's write it out. So we've got cos a plus b. So that's going to be up to the formula sheet. So cos a plus b. So that's this guy. Okay, so I'm going to write this over here, as much room as we can. So this will be cos pi over 4 times cos pi over 3 minus sine pi over 4 and then sine pi over 3. Okay, so now the good news is I know what all these things are, so I can actually put in an actual value for them. So we're going to write, so this first part will be cos at pi over 2, that's 45 degrees, right? That would be root 2 over 2. And then cos pi over 3, so the x value at pi over 3 would be a half, minus, and then sine at 45 degrees, or pi over 4, would also be root 2 over 2. And then sine at pi over 3 is going to be root 3 over 2. And then we'll just kind of clean this up, right? So I'm going to look at this one on its own first. So this would be the same thing as just root 2 over 4 minus, this would be root 6 over 4. So this one looks a lot like the last one, but backwards, isn't it? So this ends up being root 2 minus root 6 all over 4. And we just leave it like that. All right. Now we'll try it. So tan, okay? So, all right, so we got tan of 165 degrees is equal to, so let's rewrite this as tan of, and then, all right, so I just got to find some numbers that work out. Well, one thing I probably should have mentioned before, there's not like the right numbers to use here. You can actually use anything, right? We could actually find a number that was bigger than, 7 pi or pi over 12 and then subtract it. There could have been some bigger number minus something to get this, right? And we just would use a different trig identity, but it'll all work out. So there's no wrong way to do this. We just have to make sure that they're numbers that we know. So let's do this one for tan. So we'll do 45. So 45 degrees plus, and let's do 120 degrees. Okay, so then that one, I've got tan 40, so I'm adding this time, right? So I just got to go make sure I'm using the right one. So we're using the one where we're adding. Okay, so this one. Okay, so from here we've got, this will turn into tan 45 degrees plus tan of 120 degrees all over 1 minus tan 45 degrees times tan 120. Okay, so let's fill in what we know. So the good news about using 45 degrees here, right, was that tan 45 is always kind of a nice number, right? Because at 45 degrees, the opposite and the adjacent are always going to be the same, right? Either the x and the y will always be the same number. So your sine over your cos will end up always being 1. So that'll be 1 plus, and then tan at 120 degrees. So just to get a reference here, So at 120 degrees, we're talking about here, right? So this will end up being root 3 over 2 divided by negative a half. So that would end up being negative root 3, right? In the end, if you divided those. So negative root 3. And then that's over, so now I'm just doing the bottom. So that's going to be 1 minus, and then tan 45 again is 1. And then tan 120 would be, so times negative root 3. All right, so now let's just clean that up a little bit. This is the same thing as 1 minus root 3 over, and then 1 plus root 3. Okay, now that's right. That is the answer, right? But we don't like these things having these square roots in the bottom, right? We want to rationalize this thing. So I'm going to take you guys way back to Math 20-1 when we had to rationalize these guys when it's a binomial like this, right? So maybe you remember how to do this, maybe you don't. So let's just kind of follow along with me if you forget here. So what we have to do here is we want to multiply by what's called the conjugate pair. Okay, so here's your conjugate pair. So that's going to be 1, and then instead of addition, well, that was weird, we're going to subtract. So it's going to be 1 minus root 3. And then we're going to do that on the top and the bottom. So 1 minus root 3. And then we'll expand all this out and see what we get. There's a reason why we used it. You'll see what's going to happen is it'll get rid of our square root there, right? So, okay, so on the top here, we're going to end up getting 1 minus 2 root 3 plus 3. All right, that's what the top would be. So that's just doing the rainbow, right? So that 1 times 1 is 1, negative root 3, or sorry, 1 times negative root 3 is negative 1, and then that happens again. That's where we get the negative 2 root 3. And then very last thing, we went negative root 3 times negative root 3. So square root times the square root, we just get what's underneath, right? You just get that 3 back again. Okay, so that's what that becomes. And then on the bottom, this is the whole point, is that when we multiply this guy in, we end up with a canceling effect, right? Because one's positive and one's negative. Here, I'll just maybe do that to remind you why this works. So this would be 1 times 1 is 1. And then 1 times negative root 3 is negative root 3. And then root 3 times 1 is positive root 3, right? And then root 3 times root 3 is going to be just plus 3. And it's right here is the whole reason that we did the conjugate pair thing. That's 0, right? Those cancel each other out. So the bottom here would just be, 1. Oh, my bad. Root 3 times negative root 3. Sorry, that should have been minus. Maybe you guys were seeing that. Okay, so 1 minus 3. Okay, and then just cleaning that up, we'll just combine the 1 and the 3. So we'll get 4 minus 2 root 3. And then all over, and then so 1 minus 3 is going to be negative 2. Okay, and then that's pretty good, but actually we can even go one more step. I can factor the top here, right? You've got 4 and you've got 2 in these terms, right? So what I'm going to do is I'm going to factor out a 2 out of that. So we'd have 2 times 2 minus root 3 over negative 2. And then now we can cancel this, right? So the 2's cancel. So we've still got, so this will be negative because we're dividing by a negative here, right? So we've got, it'll be negative 2 minus root 3. And then just simplifying that, just distributing the negative into this, this is the same thing as negative 2 plus root 3. And there you go. That's our perfect answer. That's the way it should be written, most simplified, right? All right, so next one says, prove that sine pi over 2 minus theta, right, some angle theta, we don't know what it is just equal to cos theta. Okay, so the best way to do these ones is to write this one out, expanded form using our identities up there, and see if we can just like whittle it down to cosine theta. Okay, so I'll show you what I mean here. So this is like our A and this is our B, right? So we're going to use the appropriate identity. So we'd write that out as sine pi over 2 times cos, and then I don't know b, so it's just going to stay as theta, and then minus cos pi over 2, and then times sine of theta, and then that's supposed to be equal to cos theta. So let's see if it actually does, right? So let's just fill in what we know. So sine of pi over 2. So sine of pi over 2 is, well, that's 90 degrees, right? So that'd be 1 for my y value, or my sine value there, right? So that's going to be 1 times cos theta, okay? And then minus, and then here's where the magic happens. Cos pi over 2. Okay, well, my x value at pi over 2 is 0. So that's 0 times sine theta. So now, even though I don't know what sine theta is, I do know it's being multiplied by 0, so it doesn't really matter. That canceled. So we end up with cos. So we end up with just, on the left side here, 1 times cos theta, or just cos theta is all that's left, is equal to cosine theta. All right, next one says, given sine A is equal to 5 over 6, and cos B is equal to 5 over 13, where A and B are acute angles, determine the exact value of cos A minus B. Okay, so here's what we're going to do. Let's write this one out, just to kind of see what we're dealing with. I want to write this out in the expanded form. So let's write cos A minus B, and we'll write what that's equal to. So that's the same thing as cos A, cos B, plus sine A, and then sine B. Now, we just want to kind of fill these all in. I want to know all of those, and then I would have my answer. And they've told us 2 of them, right? I know that sine A, like I know this one, is equal to, maybe I'll even write it in there for a second, that's going to be 5 over 6. And then cos B, so cos B would be 5 over 13. So we know both of those. We don't know what cos A and sine B are, though, right? So here's what we got to do. We got to make a little triangle and see if we can figure out a bit more information to find cos A. So let's see what we're dealing with here first. So sine A, so sine, right, is equal to opposite over hypotenuse, or my x over my r. Oh, not x, y. Y over my r. And we also know, just using the cast rule, right, where is sine positive? So if I'm doing cast, then this angle here could be in this quadrant or in this quadrant. But it did say where A and B are acute angles, right? So this is an acute angle. It's less than 90 degrees. It can't be this angle. That would be an obtuse angle. Okay, so we know that it's in quadrant 1. Okay, so here, I'm just going to erase that. And that'll be for the other one as well, right? So what we can do is I can make my triangle. I can do better than that. Okay, so I know that the R value, right, this will be 6, and my Y value will be 5. And then it's really this value down here now that's going to help me figure out what sine, or what cos of A is, right? Which is what I want. I want to know what cos of A is for that one. So let's figure out what the missing length is here, right? So this would just be, call that x for a minute, would be, so x squared is equal to 6 squared minus 5 squared. So x ends up being the square root of 11. Okay, so I'll just write that in there for a minute. Okay, so we got that piece of information. So that was for angle A. Maybe write this here so we don't forget. Now angle B was also in the first quadrant here. Well, actually, you know what? Let's actually just fill this in so you can think about what we're doing here. So now remember, I was after cosine A, right? Now we have enough information because cos is equal to adjacent over hypotenuse. So this is really just, so cos A is really going to be a root 11 over 6. Okay, so good. So this here, we now know is square root 11 over 6. Now we just have sine B to figure out. So let's make another triangle. Okay, so that's going to be something like that. And then we know that this will be, well, so for cos b, that's going to be the like adjacent or my x value over my r value. So we can call our hypotenuse or our r value 13. And then 5 would be on the bottom. Okay. And if we do a little bit of Pythagorean theorem there, then this ends up being 12. So we end up getting 12 on this side. So y is equal to 12 from doing that. Okay, so then once we have that figured out, then sine b is equal to opposite over hypotenuse. So this is really going to be 12 over 13. Okay, so that's what this is. So this will be 12 over 13. And now we're pretty good to go. We actually just put all that together, right? So this would be root 11 over 6 times 5 over 13 plus, and then 5 over 6 times 12 over 13. So this ends up being 5 root 11 over 78 plus 5 times 12 is 60 over 78. So this would all become 5 root 11 plus 60 all over 78. And we'll just leave it like that. All right, next one. So given that cos A is equal to 3 over 5 and cos B is equal to 5 over 13, where angle A is between 0 and pi over 2, so that's like in quadrant 1, right? So quadrant 1. And B is between 3 pi over 2 and 2 pi. Okay, so that's in quadrant 4. Find the exact values, the exact value of cos A plus B. Okay, so, right off the bat, we know we're going to have to use these things to find the other side of the triangle, right? So let's just figure those out now. So let's go, so if I was to make like a, there's my first quadrant, then angle A is going to be over here. And then, so yeah, if I'm looking at A, 3 is going to be like my x value, right? So that's the value down here. So 3. And then I don't know my y, but I do know that my r value here is going to be 5. Okay, so let's solve for the y. Okay, so that would just be, well, this is actually a 3, 4, 5 triangle, wouldn't it be? So you can use Pythagorean theorem again. I'll kind of cut to the chase here, especially for time. This is going to end up being 4 if you solve for that one. Okay, so now we know that. Now let's do the next one. So if we did in the next quadrant, so in quadrant 4, right, that's where B is going to be. So that's going to be down here. Then we'll find this one and this one. And again, it's cos, right, that we're looking for. So this would be 5, which would be this part, right? This is 5. And then 13 is our hypotenuse. And I'm looking for the green one again, right? I'm looking for my y value there. So again, if you do Pythagorean theorem, I'm kind of skipping that just for time's sake, like I said, you end up getting 12, right? Just doing it as you should. But just be careful here because we're going down, right? This is like a negative value going down, so it's going to be negative 12. Okay, so careful in that. That would be definitely a place to make a mistake, missing that it would be negative there. And we just know that because of the quadrant that it's in. Okay, so knowing that, we can kind of just piece this thing all together now. So let's write out cos A plus B, and then write out the equation for it. So that's the same thing as cos A times cos B minus sine A sine B. And then just one by one. Cos A. All right, actually no cos A from the beginning, don't I? that's just 3 over 5. And cos B, I already know that one too. That was 5 over 13. And now it's these two that I have to like kind of think about. So sine A. So sine is opposite over hypotenuse, or y over r. So that's going to be 4 over 5. And then times, so sine B, so now I'm looking at this one. So now this one will be negative 12 over 13. And there we go. Got all of our numbers there. So if you put all of that in, you know, do your due diligence, you end up adding here, right? Because we're subtracting a negative. You get 63 over 65. Okay, next part. Double angle identities. So next whole group, right? We're just flying through a bunch of formulas now. So the double angle identities will be situations like this where you've got like sine and then 2 times the angle, and then that's going to be equal to, you know, these different variations, right? So again, for the most part, you're just kind of like looking for these different situations as you go. So let's see. So it says write the following as single identities. Okay, so I'm trying to match this up to something on my sheet, right? And it does in fact look a lot like this first one, doesn't it? 2 sine theta cos theta, and I got 2 sine and then the same angle. It has to be the same angle for both for this to work, right? But then that would be the same thing as just writing out sine, and then here I'll just write the formula first, 2 times the angle, and then my angle was pi over 3. So this is the same thing as sine times 2 pi over 3. Nothing to it. Okay, let's see again. So now we've got 2 cos squared of 7 minus 1. So now I'm trying to match this one up again too, right? And again, it looks just like that one, doesn't it? So this would be the same thing as cos 2 theta, and then that would be cos 2 times, and my angle here was 7, so times 7. So this would be the same thing as cos 14. All right. So now this one, that doesn't look quite right, does it? Tan 25 plus tan 25. I don't have any of those. But just remember what we're dealing with. If I have tan 25 and then I have another tan 25, how many tan 25s do I have? Right, you can just combine like terms there. We have 2 times tan 25 degrees over 1 minus tan squared 25. Now this does look right, right? So this would be so I can rewrite this now as tan. Here, we go right over here. Tan of 2 theta, and then my theta was 25, right? So that's going to be 2 times 25 degrees. So then this will be tan of 50. All right, now we're going to use these to prove some following identities again. So now we're going to be using our new formulas to kind of piece some stuff together. So let's go. So we got sine squared theta is equal to 1 minus cos 2 theta over 2. Now, once we start getting into these, there's actually multiple ways that we're going to be able to solve these things again. This is just one way. So maybe you find a different way that works as well, and that's fine, but I'll kind of stick to this one. So we've got sine squared theta, so I'll just leave that on this side for now because that seems pretty simple right now. I don't want to mess around with that too much. And that's equal to, now this one. So I'm going to start looking. Okay, so here I put a bunch of our formulas on the side here for us to see. I'm kind of on the hunt for something to do with this, right? So I'm looking, okay, this double angle identity, probably something to do with that, right? So let's start looking for a cos 2 theta. So I got a few, right? So I got a few options here. I got all 3 of those that I could possibly use, right? So which one do I use? Well, I want to kind of use one that seems like it's going to be to my advantage here. So I kind of look back at my other side. I'm like, okay, I got sine theta, Okay. Well, I've got sine squared theta, sorry, and I've got sine squared theta on this side too. This seems like it's getting me in the right direction, right? Because if I use this one, then I still have cos, and then I'm going to have cos on the right hand side and sine on the left hand side. Like, at least if I, use this one or this one, actually it might not be such a bad idea. You could use this one, but then you'd have to do some other kind of messing around. But this one seems pretty good. I can just pretty much change that cos into a sine, and that's what I'm after. So I'm using this one. So instead of cos 2 theta, or alpha or whatever in that case, then yeah, I'm going to write that. So this will be. So now just careful on this, because this was just this part of it was that identity. So I'm just replacing the cos 2 theta. So this will be 1 minus, and then this is where I'm going to insert that identity. So this is going to be 1 minus 2 sine squared theta, and then over 2. Okay, and then we'll just kind of simplify that out, or simplify that up. So sine squared theta is equal to, and then if we, distribute the 1 or whatever, you can end up seeing that the 1's cancel, and we would just have 2 sine squared theta over 2. So those cancel. So again, we end up proving that this identity is true. Okay, next one. Okay, so next one here. So, all right, cos theta plus sine theta, and then it's all squared. And then look over here. I don't really have anything to do with, like, both of these things squared, right? Like, it kind of looks like this, kind of looks like just our Pythagorean identity, but it's not quite, is it? All right, so I think all we have left to do, or all we can do here, is just expand this thing out. Okay, right panel work. Okay, so if we foiled this all out, right? So, because we're just squaring this, so you'd have to write it out. Like, you have to be a cos theta plus sine theta times cos theta plus sine theta, right? And then foil everything. We would end up getting cos squared theta plus, and then combining your like terms in the middle when you were done would be 2 cos theta sine theta plus sine squared theta. And that's supposed to all be equal to 1 plus sine 2 theta. Okay? I hope I didn't lose you guys on that last part. Maybe I'll just do it quick. Let's pretend that this was just like x plus y squared. What I did there is it was just like x plus y times x plus y. We'd expand all of that, and we'd end up getting x squared plus 2xy plus y squared, right? So we just got the same thing, but with cos and sine instead of x and y. Okay, now let's see if we can do some stuff with this. So look at this. We've got cos squared theta plus sine squared theta. So if I just take that part on its own, that's just equal to 1, right? So that would just be 1. And then plus, and then I just got that left. So 2 cos theta sine theta. And that's equal to 1 plus sine 2 theta. All right, so I'm kind of thinking, all right, I'm close, right? I got 1 plus something, 1 plus something. Really hoping that this just is an identity for this. And it turns out it is. So I'd be looking down to my sine 2 theta. There's only one of those. And it is, so perfect. 2 sine theta cos theta. So exactly what we're looking for. So you can change either one. So I'll change maybe this one. So I'll say this is the same thing as 1 plus 1 plus sine 2 theta and that's equal to 1 plus sine 2 theta. So good. The left side is equal to the right side. So that is an identity. Okay. Okay, so you're probably getting the idea now that these are a bit of a puzzle that you just kind of need to play around with. So, yeah, let's keep going with this. So sine 2 theta. So I'm going to look at my options here. Okay, so sine 2 theta. So let's think about this. Or sorry, not sine, cos 2 theta. So cos 2 theta, I could change it into one of these guys. This one, or this one, right? So I have a few options there. So you know what I'm going to do? I'm actually going to start simplifying the right side first, and then see if I can, if you know what it turns into. Kind of reminds me of any of these guys. Okay, and we'll kind of go from there. So this first part, a good strategy is to change these tans and these secants into sine and cos. That kind of, you know, gets us on the right track here. So, okay, so let's rewrite this. I'll say this is 1 minus, and then instead of tan squared theta, I'm going to write this as sine squared theta over cos squared theta. And then this is all over, and then secant is just 1 over cos squared theta. Okay, now I'm going to do my little trick on the top here where we can write this all over a common denominator. Okay, so that would be the same thing as, well, I can just multiply the top and bottom on this side, right, by cos. Cos squared theta, actually, cos squared. Cos squared theta. Okay, so top and bottom there. Okay, so then I can write that all over a common denominator on that step of, this would just now be cos squared theta minus sine squared theta over cos squared theta, right? Just writing it over a common denominator, right? So that's that bottom right now. That's what this is. Okay, and then that is all over 1 over cos squared theta. So now maybe you can see it from here, or maybe you need to flip it, right? Because if you divide by a fraction, the same as multiplying by the reciprocal. But either way, you're going to end up canceling those guys, right? And we're just going to end up with cos squared theta minus sine squared theta. And then I'm just kind of keeping in my mind that that was one of our identities, wasn't it? So that's what we've ended up getting it down to. So yeah, let's change this into that, right? Like that was just one of our identities. So we can say that's equal to cos squared theta minus sine squared theta, right? That's what this is. So then, yeah, in the end, I won't write it all out again. The left side is equal to the right side. Now, I do want you guys to recognize, though, we could have solved that in a different way. Maybe it's worth it. You'll need to write this down, but I just want to show you that you could have solved this in a different way. I want to show you that we could have started here and got down to cos squared theta minus sine squared theta, doing it in whatever method you like. So I also could have said this was 1 over tan squared theta over, yeah, secant squared theta. We'll try this. Why don't we write this out instead of all being over secant theta? Let's write this as 1 over secant squared theta minus tan squared theta over secant squared theta. And then I'll say, okay, 1 over secant squared theta, well, that's really cos squared theta. Okay, and then tan squared theta is really sine squared theta over cos squared theta over, and then secant theta is really just 1 over cos squared theta. And then look at that. The cos squared thetas cancel. And we end up again getting cos squared theta minus sine squared theta. So I just wanted to show you that there is no right way of doing it, right? There's lots of ways. We could have changed this cos 2 theta into something other than this too, and then we still should have been able to simplify it down to whatever, just as long as one side is equal to the other side. Okay? Okay, so now these ones say, find the exact values without using a calculator of sine 2 theta and cos 2 theta if tan theta is equal to negative 3 over 4, and theta is a quadrant 4 angle. All right, so let's sketch this to see if we can make sense of it. So tan is equal, so it's negative 3 over 4. So that must mean that that would be our positive value. That would be a 4. And then down, right, would be negative 3. Right, that would give us our negative 3 over 4, right? And they told us that's in this quadrant. So, okay, so that's the idea. And we're dealing with this angle. Now, if that's the case, this is a 3, 4, 5 triangle, isn't it? So I know you can use Pythagorean theorem again, but this should end up being 5 for my hypotenuse. Okay, there, all right, there 4 to make sure we know that that was the one we solved for. Okay, so then from that, well, you know what? I won't do anything yet until we actually kind of write these out and see what we're dealing with. Okay, so let's write out sine 2 theta and what that is. So sine 2 theta can be written out as 2 sine theta cos theta. And this is the reason why we're doing this, is because I don't know what sine 2 theta is, 2 times the angle, but I can, you know, just using these identities, or using these sides of a triangle, I can quite easily now figure out what sine theta and cos theta are, right? So that's why this is going to be helpful. So now if we just fill this in, this will be 2, and then sine theta is going to be, well, sine theta would be negative 3. Yeah, negative 3 over, so negative 3 over 5, right, for sine. And then times, and then cos theta would be 4 over 5. So that's going to be negative 24 over 25. All right, so that's sine 2 theta. Now let's figure out cos 2 theta. So cos 2 theta would be a similar method. So cos 2 theta is going to be equal to, now I could actually use, there's a few for cos, right? So I could actually use, well, really any of them. Yeah, I'll use this one. We'll say that it's cos squared theta minus sine squared theta. Okay, because cos squared theta would really be just the same thing as 4 over 5 squared minus, and then sine squared would be negative 3 over 5 squared. And now, since I'm squaring this, remember, so negative 3 squared is going to make that positive, right? But in the end, if you do that, we end up getting 7 over 25. All right, so now we're going to verify the identity for, you know what, for the sake of time here, because I can tell how long this video is lasting, we're just going to do it for just pi over 4. And then we'll prove the identity and state any non-permissible values. So let's verify this first for pi over 4. So we're going to write this out, I'll write it over here, as, here, we'll say verify for pi over 4. All right, so this would be tan of pi over 4 times sine pi over 4 plus cos pi over 4. And that's supposed to be equal to secant pi over 4. Okay, so tan of pi over 4, well, we know that one. That's like 45 degrees, right? So that's 1. All right, sine pi over 4, that's root 2 over 2. Plus, and then cos pi over 4, that's also root 2 over 2. Okay, and that's supposed to be equal to. Now, a good way to do these ones is to think about, okay, secant is like is just 1 over cos theta, right? So it's like 1 over cos pi over 4 in this case. So if cos pi over 4 is root 2 over 2, then this would actually just be flipped upside down, right? If that makes sense. So this would be the same thing. So instead of it being root 2 over 2, though, it's going to be 2 over root 2. Okay? But Again, I'm not going to leave it that way. Let's write this rationalized. So this would be, here, I'll multiply the bottom and the top by root 2. So this would become 2 root 2. 2 root 2 over 2, or just root 2. Okay, so now I know that's kind of what I'm going for over here, right? And let's see what we get. So if we got root 2 plus root 2 over 2 plus root 2 over 2, then that would be 2 root 2 over 2, right? Just keep them over the same denominator, and then those cancel as well. So we get root 2 is equal to root 2. So that one does verify. Okay, so now let's prove this. Okay, so I'm going to write it out again. So we've got tan of the angle times sine of the angle plus cos of the angle is equal to secant of the angle. All right, so let's play around with this. So let's rewrite now the tan in terms of sine and cos. So that would be the same thing as sine theta over cos theta times sine theta plus cos theta. And let's rewrite the secant as 1 over cos theta. Okay, so now kind of look here thinking, okay, what can I do here? What do I have for options? Maybe it'd be a little bit clearer. Maybe I'll write one more step here. Let's rewrite this guy. You know, I can combine that. That'd be the same thing as sine, sine squared theta plus cos theta. And this was all, or sorry, no, not yet. And that was over cos theta, just under that one, is equal to 1 over cos theta. So then, because I've done this a few times, I'm seeing a little bit of potential happening here where I've got, okay, sine squared theta, and I've got a cos theta. That might turn into 1, right? I'm kind of hopeful that I can turn that thing into 1. So what about this? Why don't I put these guys both over the same denominator? Okay, so what I'm going to do is I'm going to multiply this by cos theta on the top and bottom, cos theta and cos theta, right? So we can write that all over one denominator. So look at this, cos squared theta pops out of that. So we've got sine squared theta plus cos squared theta, which is when you're happy, over cos theta, right? Just writing it over one common denominator now at that point. And that's supposed to be equal to 1 over cos theta. And now the top, well, that's just 1, right? So we got 1 over cos theta is in fact equal to 1 over cos theta. So you would say the left side is equal to the right side. All right, and then lastly, we want to find our non-permissible values. So NPVs. Okay, so the only place that we really are dividing by 0 here that have the potential to is really at cos, right? It's because of that one and it's because of that one. So we just have to make sure that we account for that. So cos theta is not allowed to equal 0. Okay, so then where does that happen? So that would be at pi over 2 plus pi n, where n is a member of the integers. I don't think I'm going to be able to get this done under an hour. All right, let's do some more identity proving. Okay, so let's write this one in terms of sine and cos if we can. 1 over tan theta, right? I could write this out now as 1 over and then sine theta over cos theta. But 1 over tan theta, that's really just the same thing now as cos theta over sine theta, right? That really is cotan theta, isn't it? Okay, so then that plus, and then tan theta is really just sine theta over cos theta. And then I want that to be equal to 1 over sine theta cos theta. Okay, so now if we write this guy all over a common denominator by multiplying this side by cos theta, top and bottom, cos theta. And this side, top and bottom by sine theta. Then look what happens. We end up with cos squared theta plus sine squared theta all over cos theta sine theta, and that's equal to 1 over sine theta cos theta. And again, you got to love it when this happens, right? Cos squared theta plus sine squared theta. Well, that's just 1. So 1 over cos theta sine theta is in fact equal to 1 over sine theta cos theta. And those really are the same thing, aren't they? They're written the other way around. Yeah, I wrote it the other way around, but I don't know why I did that. Oh, it's because I had it written like that to begin with, but either way, those are the same thing, right? Okay. Next one. So we've got, so looking at this one, yes, so what can we do? Well, looking for just things to try here. One thing I'm noticing is that we have sine in this one and sine in this one. So why don't we try factoring out one of that sine, right? And that might be good too, because we're going to end up with like a 1. And you'll see in a lot of these, right, that we have like 1 minus something or 1 plus something. So that's probably a good place to start here. So let's factor out sine theta. And what we're left with then is 1, right? That's what I was talking about there, minus cos squared theta. And that's supposed to be equal to sine theta to the power of 3. So now, it might not be so obvious, but and you have to practice these a lot to kind of start to see when they pop up, but this one looks promising, right? I've seen things like that. So 1 minus cos squared theta. So back to my equations. So then I'd be saying, okay, 1 minus cos squared theta. Well, wait a minute. Isn't that just the same thing as that, right? If I just brought the cos squared theta over to that side, that'd be 1 minus cos squared theta. So that's all equal to sine squared theta, right? So that's good news because, you know, if you kind of think about what we were looking for there, I was trying to get more sine squared thetas. I was really hoping that this would end up being sine squared theta. So this is sine theta times, and then that is all equal to sine squared theta, which is equal to sine cubed theta. So then they are, in fact, equal to each other. Okay, and so they work. All right, so on this guy, you know what? Typically when we have things squared like this, like it's all squared, our only option here is actually just to expand everything. So this one's going to get pretty long. So, all right, so if we do this, we're going to end up with sine squared theta plus 2 sine theta cos theta. All right, that's just like the middle after we expanded it all out. And then plus cos squared theta. You guys are kind of maybe seeing the pattern because we did one like this already where the sine squared and the cos squared, that's gonna equal 1, which will make life easier. Okay, and then we've got minus, and then we'll do this next part. So I'll just do the same thing again, right? But now this time we're gonna have sine, so sine squared theta, and then this time it'll be minus 2 sine theta cos theta, and then plus cos squared theta, cos squared theta, and then in the bracket there, and that is all supposed to be equal to 2 sine 2 theta. All right, let's see if we can make any sense of this. There's gonna be some things happen. So here, I'm gonna write it all. It sucks, but I'm gonna write it all out again. So let's write sine squared theta and just distribute this negative into this one is all I'm gonna do here. So that's gonna be sine squared theta plus 2 sine theta cos theta. Minus, not minus, plus cos squared theta, and then minus sine squared theta plus, now like I'm distributing that in, so 2 sine theta cos theta, and then minus cos squared theta. It's supposed to be equal to 2 sine 2 theta. All right, now the fun part. Now we actually get to start canceling some things, doing some stuff. So do you see that we have going on here? Well, right here I've got sine squared theta, and I've got minus sine squared theta, right? I could have, yeah, turned that one into 1, but, you know, it would have worked, and I could have turned that into 1, and they would have canceled. But I think it'd be easier if I just go sine squared theta, canceling with minus sine squared theta. And then I look at my cos, and I've got cos squared theta, cancels with the other cos squared theta. And what do I have left? Well, I've got this chunk, and I've got this chunk. So this chunk here, 2 sine theta cos theta, that one looks familiar, right? So 2 sine theta cos theta. Let's see if we can remember what that was. Where's my, yeah. Right, that's this, right? 2 sine theta cos theta. So let's see if we can make any sense of that. Oh, wrong one. So 2 sine theta cos theta, that's actually just sine 2 theta. Okay, so is this one. That's also sine 2 theta. And that is supposed to be equal to 2 sine 2 theta. And it really is, right? Because we're adding these in the end. So if I've got 2 sine theta plus another 2 sine theta, I have 2 sine 2 theta. And that's equal to, yeah, the other side too. So the left side equals the right side. Last one. All right, so if I'm looking at this one, there's different ways we can go, right? I could try to change these into things, right? But again, it's probably going to be easier if I start changing these tans into sines and coses. So let's do that first, and then maybe decide what we want to do with this. Okay, so tan squared theta. So we're going to rewrite this as sine squared theta over cos squared theta, and then that's minus 1. And then on the bottom, we're going to do exactly the same thing. So this will be sine squared theta over cos squared theta plus 1. We're going to do that nifty little trick here where we're going to put this all over one denominator, right? So I'm going to multiply the bottom here by cos squared theta and the top by cos squared theta. Okay. And you know what? While we're at it, why don't we do the bottom too? Because we're going to be doing the same thing, right? So, okay, so this will be, yeah, cos squared theta and cos squared theta on the top. Okay, so that's what that'll become. So now let's write that all out. What do we got left here? So the top here, right, all over the common denominator, the first one's going to be nice, right? So I've got sine squared theta minus cos squared theta all over cos squared theta, right? That was our first chunk, right? That was the top. And then over, and now sine squared theta plus, I always like that, cos squared theta. And I always like that because that's 1. I like 1. Okay, and then that's over, and then cos squared theta. Okay, so that chunk. Now, again, you can see what we're dealing with here. If I like flip those upside down, maybe you're starting to see and be able to do that without actually flipping them. So those, my cos squared thetas would cancel. And in the end here, I'm going to get sine squared theta minus cos squared theta over sine squared theta plus cos squared theta. Now this sine squared theta plus cos squared theta, that was just 1, wasn't it? So that's just equal to 1. So the top, so we just have the top now. It's just sine squared theta minus cos squared theta. Now maybe it's a good time to start looking back to what we're trying to turn this into. we're trying to turn it into this, right? Or something like it. Or maybe we have to do a little bit of fiddling with this too. But yeah, what about this? Why don't we... So here, you know what? Yeah, let's bring this down so we can kind of look at it a bit closer. So we've got 1 minus 2 cos squared theta. All right. So different ways to do this now. So I'm looking at this one. I'm looking at this one, and wish I had this closer, but up here somewhere. Yep, there we go. I also see that, you know, that's the what I have on the one side, and that's pretty much what I have on the other side. So I could go that route, or what I think I'm going to do is, if I'm looking at this, I see that this is going to be, you know, it's cos squared theta. If I could just change this sine into a cos somehow, we'd be good to go, right? And you pretty much always can, because we can use the Pythagorean identity, right? Sine squared theta plus cos squared theta is equal to 1, right? So sine squared theta is equal to 1 minus cos squared theta. So let's replace the sine squared theta with 1 minus cos squared theta, and then minus cos squared theta. And here we see that would end up being 1 minus 2 cos squared thetas, which is exactly what we have on the other side, 1 minus 2 cos squared theta. And there you go. Like I said, you could have done that many ways, but that's one way. All right, go take a break if you watch that whole long video. That's definitely the longest one, I think, of the course. So see you in the next one.